Hey math people, I got a really interesting topic for you today. 3 mathematically awesome facts on bowling pins. So don't exit out yet. I promise you I will do my best to make this idea fun because it is. The arrangement, or I guess the setup of 10 bowling pins in a bowling alley, creating that triangle, has some really cool ideas attached to it in terms of the math. And it is my job right now to prove it to you. So I got 3 ideas that come into play with this. Let's start with the first one, which is the number of combinations that come into play with those 10 pins. Let's go. Okay, so the first idea came into play when I was bowling a few weeks back. Obviously, when you bowl, you have all these pins that go down, right? That's a thing. And sometimes not all of them go down at once. In fact, very often, when you're a novice like us, you'll have only a few going down, or maybe none, or maybe all of them. And that's the idea that I wanted to explore. How many unique combinations of bowling pins can there be in a standard 10-pin setup? So as you bowl through 10 pins, sometimes a few fall, sometimes none fall, and sometimes they all fall. So I want to figure out how many different combinations can there be of these 10 pins standing up. Now I'm going to show you 2 solutions. One way I worked through, and the other is a much better approach. It's a little easier to comprehend. So what I did was I borrowed from logic that came into play in combinations. So that's usually taught in either an Algebra 2 or Pre-Calc course. And the idea behind combinations, I'm not going to go too deep into it, but it's generally this. If you have 10 things to choose from, and you want to choose, say, 5 or 6 of them, these pins are all unique. You have pin 1, pin 2, pin 3, pin 4, 5, 6, all the way up to 10. How many different ways can I choose 5 of those pins? Well, there's many, right? You can choose the first 5, you can choose the later 5, you can choose the outer 5, or you can choose the inner 5. So you play around with that idea. So that's exactly what I did. So my inferior solution here, I'm going to move it a little bit, was I considered, well, if you have 10 pins, what if you choose 0 of them to stand up? How many different combinations do you have? Well, 10 choose 0. If you're choosing 0 of 10, how many different ways can you choose 0? Well, only once. So this 10 choose 0 idea, that's the notation and how it's read, would simplify to just 1. With this 10 choose 1 idea, if you have 10 pins, in how many ways can you choose one of those 10 pins? Well, you can choose the first one, you can choose the second, you can choose the third, fourth, you can choose any of the 10. So there are 10 different ways to choose 1 pin of 10 pins. So 10 choose 1 simplifies to 10. And this idea, I'm not going to go through every single term. There are 10 terms here. I just computed this idea all the way through and through, and all the way up to the last one, 10 choose 10. If you want to choose 10 of the pins, how many different ways can you choose 10 of 10? Well, obviously 1. If you add up all these numbers, it comes out to 1,024. This way sucks. This way was a lot of work on my end. So I asked one of my friends who is a part engineer, part med student. He's kind of a double 2-for-1 type of person in that regard. And he came up with a much more elegant solution. I'm going to show you that right now. Okay, and time for a much simpler approach. Let's break it down to the most simplest case possible. What if you only had 1 pin? If you have 1 pin, how many different combinations can you have there? Well, think about it. 2. And some people are thinking 1, but you can either be standing or not standing, right? Standing, not standing. 2 different combinations. That's what I played around with here. When you have 1 pin, it's 2 to the power of 1, which is 2. There are 2 different combinations. What if there were now 2 pins? Consider the case where you have 2 pins. Well, you have both pins. You have just the right one up. You have just the left one up. And then you have the case when they're both down. That's 4, right? 2 to the power of 2. And maybe you see where this is trending. When you have 3 pins, well, you have, okay, so let's get ready for this one. You have all the pins. You have none of the pins. You have the leftmost pin. You have the rightmost pin. You have the middlemost pin. You have the outermost 2, the inner, okay, gotta be careful with that one. The leftmost 2, and the rightmost 2. So that is 8. That brings you to 8 different combinations, which is 2 to the 3rd power if you didn't catch that already. If we go all the way up to, well, when there's 10 pins, our situation now, it's 2 to the power of 10. Would you look at that, you have 1,024 once more. This way, a lot easier to think about it. What he said was, well, a pin is either up or down, and that's 2 options. If there's 10 of them, 2 to the power of 10. And I was like, whoa, that's really smart. So a very elegant solution to what could be a very cumbersome problem if you sit there trying out every last combination. So this idea is cool, but let's talk about the the way it's set up in particular, and the shape that it creates, and the set of numbers that you're about to learn about in like 3 seconds. All right, when we're looking at a setup of pins, it creates a triangle, right? Well, that is very particular. Actually, those are called triangular numbers. So when you establish this triangular-like shape, such that each kind of next row is one higher. So, for example, the next row after the first row is 2, the next row after the next row is 3, and so on. That's a triangular number. So the number 1, when you have just one pin or one whatever you want to call it, by itself, that is a triangular number. When you then move back a row and you add another pin, so there are 3 pins in total, well, that's also a triangular number. Who would have thought that the number 3 is a triangular number? If you move back once more and you add another pin to that back row, that comes out to 1, 2, 3, 4, 5, 6. The number 6 is a triangular number. And then our classic case, what we have in a bowling alley, you move back one more row, 4 rows in total, where the back row is 4. You add that up, of course, 10 is the number of pins you have. That's actually a triangular number. You can keep going with this line of thought. Add 5 to that, you're at 15. Add 6 to that, you're at 21. Add 7 to that, you're at 28, and so on. This set, which is infinite of numbers, is called the triangular number set, or set of triangular numbers. Now, the formula for that is actually fun to play around with. It's t sub n is equal to n times n plus 1 over 2. So n here represents the number of rows. In this case, when you have just one row, obviously it's 1, and I'll show it to you. When you plug in 1 here, it's 1 times 1 plus 1, which is, well, 2 when it's in parentheses, and 2 over 2 is 1. In our case, that is 10. There are 4 rows, right? 1, 2, 3, 4. So I'm going to plug in a 4 here. 4 times, well, 1 plus 5 is, or 1 plus 4 is 5, so 4 times 5 is 20. 20 over 2 is our number 10. So this number, if you wanted to figure out the triangular number for, I don't know, 35 rows, you can plug in 35 here and it'll tell you that triangular number that corresponds with that. So telling you what that is isn't enough. I want to actually prove to you why this equation holds true, and that's what I'm going to do right now. But in order for me to do that, I need to rearrange my set of bowling pins because something will become clear when I sort of scooch them over a bit. Let's find that out right now. Okay, now it is time to prove this notion of t sub n is equal to n times n plus 1 over 2. What I've done with my set of pins, I've scooched them all over. So rather than having the shape looking like this, I've created a little, oh god, I cannot do that with my hands. I created a right triangle, and I just scooched them over like so. And you can see them, the 10 black pins here. Of course, we have that 4, 3, 2, 1 pattern going on. Here they are. I just scooted them over. The second thing that I did was I drew this dashed line, and I reflected those set of pins over to the other end. Now, this is going to be kind of weird to think about at first, but what I've done is I've established or created a second set of fake pins. So if I had 10 pins and I have 10 fake pins, you know, I have 20 pins in total. Just keep that notion in mind for now. And what I've done is created a rectangle, and we know that the area of a rectangle is length times width, after all. So in this particular case, I'm just going to add up the pins, you know, from left to right and up to down. That's going to be my length and my width. So from up to down here, I got 1, 2, 3, 4. My length here is 4. From left to right, I have 1, 2, 3, 4, 5. My width is 5. 4 times 5 is 20. And remember, I created a second half. So 20 cut in half, that's your number 10. In order to think about this more abstractly, think about that relationship between 4 and 5. To get from 4 to 5, it's just plus 1. So we're going to sort of take a step outside our boundaries and view it through the scope of n times n plus 1, rather than 4 times 5, n times n plus 1, for any number of cases that you might have. You know, you might have 50 rows, you might only have 2 rows, and this satisfies all cases. So in our event here, my length is n, and my width is n plus 1. That's the area, n times n plus 1. But the thing is, we got to cut it in half, because remember, I created a second half just for the sake of this problem. So that's exactly what we're doing here. Taking that n times that n plus 1, cutting it in half, and that's exactly how you end up getting t sub n is equal to n times n plus 1 over 2. This is the proof for coming up with the algebraic statement for triangular numbers. Kind of a long way from throwing a ball at pins. But I got one more fact for you, and it's just a fun, goofy one. The real math is kind of over, so let's get to our last one. Okay, last fun fact. Graph this thing. Graph this function. I'll graph it for you actually in the next little bit. But it reads b of x is equal to the square root of 1.2 plus 5.32x minus 1.485x squared plus 0.135x cubed minus 0.004x to the fourth. Okay, that was a lot. But if we graph this thing, something fun will emerge. I'm going to show you right now. All right, voila. So I went ahead and graphed it, and this is what you get. It appears to be a bowling pin kind of laying down. And if you were to maybe, I don't know, rotate it across the x-axis, you might get a bowling pin kind of laying down. Here, I might even, what if I play around with this idea? I'm going to take just this part, make this negative. So you can also make it negative, and you can just kind of force a reflection across the x-axis, and there you have your bowling pin graphed. So I didn't create this function, by the way. I found it here. Michigan, I guess, had a course where somebody did calculus with it. You don't need to do that, obviously, but I thought it'd be a cool idea to explore. Okay, that is all I have for you. Enough bowling math for one night. I'm going to call it quits here. Please do continue to math on, and I will do the same. I'll see you next time.